All right, so this is again the hydrogen atom. Bohr's theory was able to establish these energy levels, and it didn't really explain the wave-like behavior of electrons. So, we know that light has this dual nature. It acts like a wave, which we kind of already knew, and now it acts like an electron, which this explains. This theory couldn't be expanded beyond more than one electron. So anyway, current ideas about atomic structure depend on the principles of quantum mechanics, which is the theory that applies to subatomic particles. So that's kind of what we're talking about, quantum mechanics. Okay, so now we've been talking about how light acts like a particle, but we got to come full circle and see how the wave particle duality comes to light. So de Broglie was somebody who studied this relationship in 1925, and he said, okay, so light exhibits these particle aspects. What if all particles actually show wave characteristics? So what if everything has this duality of nature? He kind of looked at the energy formulas and set them equal to each other. So he postulated that any particle that had some kind of mass and was moving, so it had a velocity, it had an associated wavelength. Okay, so he said, okay, energy, or light acts like a wave, so we know energy is related to frequency. Light acts like a particle, meaning that it has mass and it moves at the speed of light, well, light particularly, so c is the speed of light, mv squared, mass times velocity squared, is energy. If we set these two things equal to each other, then mc squared equals h nu. If we rearrange this equation a little bit and plug in this quantity, that the wavelength and the speed of light in for frequency, we get mc squared equals hc over nu. A few things will cancel out. We can rearrange it and we find this equation. This is the de Broglie equation. It says that wavelength is equal to Planck's constant divided by the mass of the particle divided by c. If it's light, then it's the speed of light, the velocity of light. But if we're applying it to just any old particle, then we're just going to call that the velocity in general, the velocity of the particle. So we're saying that anything that has mass and velocity, any particle that has mass and velocity should have a wavelength attached to it. So let's look at an example of that. Again, this is called de Broglie's relationship. Any particle that has mass and is moving also has a wavelength. Okay, so let's apply this to something common, for example, a baseball. So the de Broglie relationship shows, so if we have a baseball, which weighs about 145 grams or 0.145 kilograms, and it's moving about 60 miles per hour, which is about 27 meters per second, it will have a wavelength of 1.7 times 10 to the minus 34 meters. We kind of have to remember, I don't know if we looked at this, or the unit joule can also be kilograms meters squared per second squared. So just think about that for a second. So if we plug it in our equation, H is 6.63 times 10 to the minus 34 joules times second. So if we plug this in, so it's kilograms meters squared per second, because it's joules times second. So this is joules times second is the same unit. And we put it like this so that the other things can cancel. So if we have joules times seconds, and then we have kilograms cancels, and 1 meter cancels, and the seconds cancel, then we end up with meters. So that's our unit, meters. That's not important. You don't need to worry about that. We won't do any calculations like this, but I just want you to see that a baseball that weighs 145 grams and moving at about 60 miles per hour does have a wavelength associated with it, but it's so tiny that it is not observable or detected. Actually, so it's kind of, as the particle gets smaller and smaller and smaller, the wavelength gets more and more into the range that is detectable. And actually, this idea led to the discovery or the creation of the electron microscope, so that it got to a point where particles could be observed. Again, so electrons have wavelengths on the order of a few picometers, 10 to the minus 12th meters. So under proper circumstances, we can see the wave character of electrons observable just barely on our spectrum. And so that, like I just said, so in 1927, it was demonstrated that a beam of electrons, similar to X-rays, could be diffracted by a crystal, and this led to the first electron microscope. So it was the first time we could actually see the wavelength of an electron, the wave property. So de Broglie kind of has this shows this duality can go both ways. It's just that it's really only observable in very tiny particles. All right, so quantum mechanics. It's the branch of physics that mathematically describes the wave properties of these tiny particles, submicroscopic particles, mostly electrons is what we're focusing on. So we can't think, we used to think that, oh, here's the nucleus and here's an electron and it's orbiting the nucleus. Well, that is not true. The electrons can't have a precise orbit in an atom. It turns out that if we want to know the exact location of an electron and its exact position, we can't, and how fast it's going, its exact position and how fast it's going, we can't. This is called the Heisenberg uncertainty theory, and it uses some higher math that we don't need to worry about. But what Heisenberg said is that it's impossible to know both the location of an electron and the speed of an electron at the same time. Either the closer you to know how fast an electron is moving, the less likely you know where it's located. The closer you're able to zoom in on where the electron's located, the less likely you can know how fast it's going. And so I guess when an electron was pulled over by a cop because he was speeding, and the cop said, "Do you know how fast you were going?" The electron said, "Oh no, if you tell me, I won't know where I am." Anyway, that's Heisenberg's uncertainty principle. And also I had a sticker in college that said, Heisenberg may have slept here, so they make jokes about it. Anyway, that's all you need to know about it, is that the closer you know the exact position, the harder it is to know how fast it's moving or what direction it's moving. The closer you know how it's moving, the less you know where it is. So we like to think of electrons as kind of in a region of where it might likely be. So this is just writing Heisenberg's uncertainty principle in a little more specific way. And it just says, momentum is mass times velocity. So what this is saying is that the change in location, or the uncertainty in the position, times the uncertainty of the momentum, which is the mass times the change in velocity, the product of these two can't be less than h over 4 pi, what pi is pi. So anyway, again, this is saying sort of the same thing. The better you know the location, the less likely you're going to know where it's going. Okay, so just a little bit more about this uncertainty. Uncertainty principle is really significant only for things that are very small. Obviously, we don't lose sight of a ball flying through the air and where it's located and its velocity. We can see it coming and we duck out of the way. But anyway, so this equation, when it has to do with really small particles, so electrons that have a small mass, the uncertainties are large relative to an atomic scale of dimensions. So anyway, it's more important for electrons and not for bigger particles. So finally, we're going to use quantum mechanics at the level that we can understand it. And although we can't precisely define an electron's orbit, we can find out what the probability of finding an electron in a certain location is. So probabilities. This all has to do with, if I could measure the electron 100 times, where's it most likely to be? I get an area that it's most likely to be. So it could be out here sometimes, but probably 99% of the time it's within this circle. So again, we can't guarantee it's in the circle, but we can figure out where it's most likely to be. And so the probability of finding an electron at any point. And these actually, using some higher math, you can actually get equations of regions in space. Using some calculus. So Schrodinger defined the probability of where an electron can be located in a mathematical expression that he called the wave function. And the wave function is given the symbol psi. So again, it uses some higher calculus. But once these functions are solved, then what we have is a defined region where an electron will most likely be found, like 99% of the time. So actually, the probability of finding a particle in a region of space is defined by that Schrodinger, that wave function squared. What this gives us is an electron density. Again, where is the most likely where is the electron most likely